So this video is going to continue Chapter 12 of Geometry. It's going to cover 12.3 to 12.5. And by the end of this video, you should know about similar triangles and some conjectures about similarity and proportionality. So we're going to start out with the Sss Similarity Conjecture, which says that if the three sides of a triangle are proportional to the three sides of another triangle, then the two triangles are similar. So say we have this triangle here with sides 3, 4, and 5. If we then have another triangle here and it has sides 9, 12, and 15, we can see that, well, here if we say these are corresponding sides, that's times 3. And again, if these are corresponding sides, that's also going to be times 3. And if these are also, it's going to be times 3 again. So they're all proportional because they're all at the same ratio. They're all 1 to 3. So now we have our AA similarity conjecture, which says that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So this is kind of cool because you're given only two pieces of information, but you're actually able to make this conjecture that the two triangles are similar. So if we have a triangle here, and say this is 70 degrees and this is 50 degrees, and if we have another triangle here, and this is 70 and this is 50, we can actually say that these two triangles are similar. And the reason we can do this is we can find the last angle because the triangle measures are going to always add up to 180. And when you have three of the same angles, your sides are, by definition, going to be proportional. So now we have the SAS Similarity Conjecture, which says that if two sides of one triangle are proportional to two sides of another triangle, and the included angles are congruent, then the triangles are similar. So if we have a triangle here, say this is 100 degrees, this is 3, and this is 2, and we have another triangle here, this is also 100 degrees, and this is going to be 9, and this is 6, then we can say that these two triangles are definitely similar. So you can use similar triangles to calculate the height of objects that you are unable to measure directly using proportions. So this is a really useful thing. So for example, if we're given that, so we have the height of a man who's 5 feet tall, and his shadow is 6 feet tall. That we can measure. But we want to find the height of this lamppost, which we can't measure, and we see that its shadow is going to be 18 feet tall. So what we can do is say, well, if the proportion of the man to his shadow is 5 to 6, then we can set that equal to the proportion of the lamppost to its shadow, so x over 18. And then how you solve proportions, a good way is how I learned it was the Jimmy Neutron method, where you circle here and you circle here, and then you multiply, you cross multiply, so you bring over the numerator. And so we get 6x equals 18 times 5. And then we can divide that by 6, cancel, and then we get x equals 15 feet. So this next conjecture is really useful. It's called the proportional parts conjecture. It says that if two triangles are similar, then the corresponding altitudes, medians, and angle bisectors are proportional to the corresponding sides. So essentially, if you have two similar triangles, then everything in them is going to be proportional, not just the outside sides that you know are proportional. And then this next one says that the angle bisector in a triangle divides the opposite side into two segments whose lengths are in the same ratio as the lengths of the two sides forming the angle. So, okay, the angle bisector in a triangle, So if we have our angle and it's bisected here, divides the opposite side into two segments whose lengths are so they're not necessarily the same, whose lengths are in the same ratio as the length of the two sides forming the angle. So the ratio of this to this equals this, the ratio of this to this. And you can see this if I draw my triangle differently. When we have our angle, you can see that this side is longer, this is longer. So let's do a practice problem with what we just learned. So if we have our triangle and we're given that this is the angle bisector here, and we know that this side is going to be 5, this is going to be 4 and 6, and now we're asked to find this side. So we just learned that the ratio of this to this is equal to the ratio of this to this. So then if the ratio is 4 to 6, we can set that equal to 5 over x. And we can do our Jimmy Neutron method, bringing over the numerators. So we get 5 times 6 equals 4x. We can divide by 4, we can switch around our sides to make it easier. And then we come out with 15 over 2, or 7.5.